Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 3, Lesson 2. So we're going to continue talking about charged things and electric charges. Last time we reviewed the proton, the neutron, and the electron, and what we know about them from previous classes. And so one of the interesting things about this charged stuff is that charged things push on other charged things without touching them. So think about that for a moment. There's something kind of magical about it. Usually when A pushes B, it's because A, my hand, is touching my cheek, and that's how hand pushes cheek. Usually we think of forces happening, A pushes B, when A touches B. And that's called a contact force. Oops, it's a new pen. It's a new pen. There we go. A contact force. So A pushes B. We have a pusher and a pushhead, or a thing that gets pushed. And A pushes B when A touches B. That makes sense. But sometimes A pushes B, but A does not touch B. So that feels like magic. You know, how can I push on this pen without touching the pen? If I were to say, pen, come here, and the pen were to jump over to me, that would be magic because we don't understand how that works, except that it does happen sometimes. When I was a small child, I had a little box full of magnets. I played with them, and it felt like magic to me because I could have a magnet here and I could have a magnet near it, but not touching it. And the magnet down here would jump up. And that just didn't feel like, you know, it comported with my understanding of the physical world, you know, as little 5-year-old Davy, because they weren't touching each other. So sometimes I call this pushing without touching. Which I think makes perfect sense. But the fancy physics phrase for that is field forces. So if A pushes B when A touches B, we call that a contact force. If A pushes B when A does not touch B, we call that a field force. And when you're a kid, you don't sit around with a box of protons because nobody has a box of protons. So these electric forces are what we're talking about right now. They are different from magnetic forces, but magnetic forces are similar in that they are field forces as opposed to contact forces. So no, I am not saying magnets are the same as electric things. I'm not saying the north end of a magnet is positively charged. I'm not saying that. But magnets, which may be part of your common everyday experience, exert these field forces. Charged things also exert these field forces. So what do I mean when I say that? I mean, if I have a little positively charged thing here and a little negatively charged thing here, they are going to exert forces on each other. This one pushes this one, and according to Newton's third law, this one pushes this one. This one, so they're oppositely charged, so we know they attract, which means this one pushes this one left. So I put this left arrow representing the force on this one. I made it purple to show that this is the thing exerting the force. If this one pushes this one left, this one pushes this one to the right. And these two forces are from Newton's third law, what we call an action-reaction pair. Notice that I made the arrows the same length. That was intentional. It's the same number of newtons, and they're in opposite directions. So every action has an equal, same length, and opposite, 2 different directions, reaction. This one pushes this one left. This one pushes this one right. How big are those forces? We talked last time about Coulomb's law, which says that an electric force, F sub E, is equal to K, which is just a number, 9 times 10 to the 9th, Q1, the amount of charge here, Q1, times Q2, the amount of charge on this one, divided by R squared, where R is the distance from one to the other. This number, KQ1, Q2 over R squared, is the number of newtons that this force is. It is also the number of newtons that this force is. So that is the Coulomb law, KQ1, Q2 over R squared. So how does this thing actually push on this thing if they're not touching? Well, it turns out that that's not a question that we're interested in answering. But it means, so the fact that this one does push this one, it's a field force. And so I'm about to talk to you about what a field is. It's more mental gymnastics. What I'm going to say is this positive purple charge, we could think of, instead of saying somehow it magically pushes this one without touching it, what I'm going to say is this positive charge changes the space around it. It inserts into the space around it this thing that we call an electric field. So because there is charge here, the space around it is now changed. It is different. It is infused. It is filled with this thing that we call an electric field. And then it is this field that exerts the force on this negative charge. Oh, similarly, this negative charge inserts into the space around it an electric field. Positive charges and negative charges are different. The field surrounding positive charges, we say points away from the positive charge. The field surrounding the negative charge, we say points toward. That just works out. We define this, again, it's just mental gymnastics. We're creating this idea. We define the field as pointing in the direction it would push a positive charge. So if I put a positive charge here, the field would push it right. If I put a positive charge here, the field would push it up and right. If I put a positive charge here, the field would push it up. Did I put a positive charge here? No, I put a negative charge here. If I put a positive charge here, the field would push it right. Since this is negative charged, the field pushes it the opposite direction, hence this arrow to the left. This negative charge creates a field pointing this way. If I put a positive charge here, the field would push it right. If I put a positive charge here, the electron would attract the proton and push the proton right. Therefore, if I put a negative charge here, the field would push it the opposite direction that it would push that positive charge. In other words, the electron would repel the electron. Does this field push this electron? No, it does not. This field was created by this electron. It's an explanation for how this electron pushes other things. The electron does not push itself. We don't talk about things pushing themselves. So that's one way of talking about the field. I did want to say about Coulomb's law. I think I said this in 231, but I'll say it again in 232. Coulomb's law says A pushes B with this arrow and B pushes A with this arrow. The phraseology that's out there is there's a force between the two objects. There's not a force hanging out here between them. When someone says there is a force between A and B, what they mean is A pushes B and B pushes A. All right, and then we can think about that in terms of these fields. So these are called field lines. And there's all kinds of wonderful things you can read about electric field lines. Electric field lines. Notice that I used the word line, even though it ends. It looks more like an electric field ray to me as a person who has taken a geometry class, but we call them lines. And sometimes they are not even linear. Sometimes they curve. For example, what if I had both a positive charge and a negative charge, and I wanted to talk about the field lines between them? What would the electric field look like on this paper? Well, let's think about how a little positive object. So I'm going to take just a little bitty plus sign, and I'm going to pretend I'm putting these little plus signs places, and I would say, well, what force would that plus thing feel? And then there must be a field in that direction pushing it that way. So if I put a positive charge here, this would push it right. And this, since it's negative, would pull it right. So anywhere in here, if I put a little plus charge, this would repel it and therefore push it right. This would attract it and therefore pull it right. So I'm going to say the electric field in that space points that direction. What about here? Anywhere along here, this plus would push a positive thing to the left. Anywhere in here, this would pull that positive thing to the right. Ooh, so I've got a force to the left and a force to the right. Who wins? Well, because Coulomb's law has r distance in the denominator, this is closer to the charges than this. So this one would win, and the field would point that direction. Similar thinking takes us over here, looking at the time. Positive charges, what effect would this have on them? It would pull them left. Positive charges, this would push them right. But since this one's closer, it wins. So these arrows are indicating the direction of the electric field. What if I had something up here? Think about if I had a positive charge here. This would push it up. This would pull it right. But this is much closer. So the field would be almost perfectly straight up. But then as I move farther away, they aren't, they get less different in their distance. And so it turns out that a positive charge would actually follow a path kind of like that. Symmetry would give me these curved, I'm still going to call them field lines, even though they're curved. So at this exact location, the field would point in a direction tangent to that line. So the field here would point up and right, maybe mostly up and a little bit right. So we could end up drawing all these beautiful curved field lines in here. And that is what the electric field surrounding two oppositely charged particles would look like. And at any location, a tangent to that curve would indicate E, capital E, the electric field. Is there really such a thing as an electric field? Does it really exist there? That's not important right now. What's important right now is that this is the way we describe the fact that these charged things push. Now, how could I find the exact electric field here? Let's talk about that. Coulomb's law says F sub E equals K Q1 Q2 over R squared. So let's say I have a charge here, Q1. And it is going to exert a force on this other little charge that I have here, Q2. So this is going to push this. This is also going to push back on this, but let's not talk about that right now. Right now, we're just talking about the force that this one exerts on this one. So that has to do with the field created by Q1. So I'm drawing these arrows. Q1 creates a field, and that field is going to push Q2. So I'm going to rewrite this as KQ1 over R squared times Q2. This and this are obviously exactly the same thing. But what I've done is I've separated out the part that has to do with this charge and the part that has to do with this charge. And what I'm going to say is, if I put a charge Q2 here, that the force exerted on it is different from if I put a different amount of charge there. If I put something here with more charge, the force would be greater. If I put something here with less charge, the force would be less. If I put something here with an opposite sign charge, the force would be in the opposite direction. So this is the push ed, the thing that gets pushed. And that's where it fits into the equation. This is about the pusher. And it turns out that this thing in the circle there, K Q1 over R squared, this is the electric field. This thing creates an electric field around it, these green arrows of this size. The electric field is K times the charge divided by R squared. In other words, more charge creates a stronger field, less charge creates a weaker field. The field surrounding this is less strong out here, because R squared is in the denominator, and stronger in here. If I go twice as far, I have 1/4 as much electric field. If I go 3 times as far, the field is 1/9 as strong. If I go 10 times as far, the strength of the field is 1/100 because of that, what we call a 1 over R squared relationship. So the electric field is numerically equivalent to K Q1 over R squared. Now let's look, that was the numerical part. Let's look at the unit. If force is expressed in newtons and charge is expressed in coulombs, well, if the unit on the left and the unit on the right have to be the same thing, if this is newtons and this is coulombs, this unit has to be, I'm going to say that again and let you try to think of what the answer is. If the unit on the left is newtons, then the unit on the right has to be newtons. But this is coulombs. So what does this unit have to be? The answer is it has to be, I'll pause, give you a sec, newtons per coulomb. Newtons per coulomb times coulombs is newtons. So the electric field has the unit newtons per coulomb. Put that in your quantity and unit table. Electric field is the quantity, the unit is newtons per coulomb. It's how hard we push per coulomb of charge that is stuck there. The per coulomb is per this number of coulombs, not per this. So that is electric field and its unit. Okay. Now, what if I have a couple different charges? What if I have a 2 plus 2 coulombs right here, and I have minus 4 coulombs right here? And I said, question mark, what is the electric field right here? What is the field right here? Well, I would have to find the electric field created by this and find the electric field created by this separately, and then I would add them together. And I would add them together as vectors. In other words, what's 3 plus 4? Well, it might be 7, but if I have 3 in one direction and 4 in this direction, then the sum is actually 5 in this direction, because 3 squared plus 4 squared is 5 squared. So, what is the electric field here? Well, if this is positive 2 coulombs, if positive charges create fields pointing away from themselves. Negative charges create electric fields pointing toward themselves. So I'm going to have these 2 electric fields that I have to add as vectors. So I would need to know this distance. Let's just call this distance x, and let's call this distance y. This electric field would be, remember, I said the electric field is KQ over R squared. So K times Q, 2 coulombs, over X squared, 2K over X squared. what is this field? Well, it is K, Q. I don't have to worry about the negative. I'm not going to put a minus there because I already took into account the fact that this is negatively charged and therefore the field points this way. So K times 4 over R squared. Oh my goodness. What is R? Over R squared. Well, this distance is the hypotenuse, right? X squared plus Y squared equals R squared. So R is the square root of X squared plus Y squared. Right? That's what R is, and it's KQ over R squared. So actually the square root and the squared make each other go away, and I get 4K over X squared plus Y squared. That's the strength of the field right here. Then what I would do is I would add them as vectors. And you remember how to do that from last year. Don't add them like this. We have to add them head to tail. So there's this one plus this one, and the answer would be this one. We're not going to review vector addition right now. You already know how to do that. But this is called the superposition principle. If there's an electric field at this location from one charge and an electric field at this location from another charge, we would individually find the strength of those fields and add them as vectors. And then that would be the net electric field. Then I'm going to show you one more equation. Electric force equals K, Q1, Q2 over R squared. You've seen that before. But then I said I can take this K, Q1 over R squared, and remember that was the electric field? So this is much simpler. Electric force is equal to electric field times charge. So I could take this net electric field, E, and then just multiply it by Q, however much charge I stick here. When I say F equals EQ, really important equation, the electric force exerted by an electric field is equal to the strength of the electric field times the charge experiencing or being pushed by the field. Not the charge creating the field. No, no, no. That already got taken care of. This Q is the charge that creates or makes the field. This charge is the charge that gets pushed by or that experiences the field. Very, very, very important distinction. Okay, I'm looking at my notes. We talked about the superposition principle and electric fields and the unit for electric field. And just to be careful, capital F and capital E kind of look alike. They're not the same. This is an electric force. This is an electric field. A force has the unit newtons. A field has the unit newtons per coulomb. They're different. It is a common mistake in physics to say one and mean the other, or to read one in the book and hear or think the other. They both start with F. They're both 5 letters long. I get it. There's nothing wrong with you if you ever make that mistake, but be very careful and try not to make that mistake because they are different things. All right, now let's just talk about something a little bit more fun, a little bit more real world-y. I don't have a balloon in my hand, but I wish I did. I thought I had some balloons in the room, but I don't. If I had a balloon and I rubbed it on my hair, you know how when I pull it away, my hair would tend to stand up because for some reason, if I just have a balloon and I bring it near me, nothing happens. But if I rub the balloon on my hair, then all of a sudden my hair is attracted to the balloon. Why is that? Well, it turns out that when we rub a balloon on someone's hair, electrons get rubbed off of one thing and on to the other. Now, I'm not going to tell you which is which. I want you to look it up in the book. But the balloon is made of rubber, and we'll call my hair fur. So rubber and fur. When rubber and fur are rubbed one against the other, what happens is called charging by friction or by conduction. Electrons leave one of the things and get transferred onto the other. And therefore, one of these things has extra electrons and is negatively charged. One of them has a deficit of electrons. Electrons got pulled away, and so the protons that were with them remain. And so one of these things is positively charged, one is negatively charged, and therefore they attract each other. And so so they are said to be charged things. And you might think, but wait a minute, the balloon at the beginning, we said it was neutral, but it was made of billions and trillions and quadrillions of little charges, but they were all equally paired. For every proton, there was also an electron. For every proton, there was also an electron. When, if there is a thing and electrons get rubbed off of it, then protons remain unpaired, and we say it's overall positively charged. If I add electrons to it, overall, it would be negatively charged. So anyway, I want you to look up either online or in your book, and when rubber and fur get rubbed one on the other, which becomes positively charged and which becomes negatively charged. Another classic pair of substances is glass and silk. And if I were wearing a silk tie, which I'm obviously not, and I had a piece of glassware from the chemistry class, I could rub the tie on the silk. And again, they would attract each other because one would have become positively charged, the other would have become negatively charged. A thing that loses electrons becomes positively charged. The thing that gained the electrons becomes negatively charged. And I would love it if you read around and knew which was which. I could just tell you, but that's no fun. And then, so that is conduction, when the electrons move from one thing to the other. Last thing I'm going to tell you is this word called induction. So let's say I have an object that for one reason or another has become positively charged, and I bring it near something that's neutral. Lots of pluses, lots of minuses. If I bring this near here, these pluses repel all the pluses on here. But positive charges are trapped in the nucleus and can't really move around. These pluses attract all the negative charges, and so some of these negatives can move closer. And so now what we have is there's still overall this object is neutral, but it has a negative side and it has a positive side. And because it has a negative side and a positive side, the negative side attracts this positive thing more than the positive side repels it, because these guys are closer. These things are attracted. And if this were my balloon, it would actually cling to the wall and stick to the wall. So I rub the balloon against my hair. I know why they attract each other, because one's positive and one's negative. But now the charged balloon would actually stick to the wall. If I could hold it up to the wall and let go, and it would stay stuck to the wall. Not because any charges have been transferred or conducted, but this is called induction, where we have induced or forced there to be a negative side and a positive side. It also would have worked if the thing I had brought near were negatively charged. Bring a negatively charged near a neutral thing, plus minus, plus minus, plus minus, plus minus. The minuses attract the protons, but protons are trapped in the nucleus, so they can't move. The minuses repel the electrons. So I have a plus side and a minus side. And notice that the plus side, which is attracted to the negative thing, is closer, and the negative side, which repels the negative thing, is farther. So this wins, the attraction wins, and again, this thing would stick to the wall. So that's called induction, when I have a neutral thing that stays neutral. but the neutral thing is separated into a positive and a negative side, meaning that the closer side will attract something and make them stick. And that's called a method of charging. Final words. These charges are moving around. If charges can move on a thing, we tend to call it a conductor. If charges can move around on it. If charges don't move around on it, we call it an insulator. And you'll notice that I put both words on the same thing. Classic conductors are things like metal. Let's just say metal. Insulators, things like rubber, wood, air. And I love air because it's my favorite example. Air, we say, is a really great insulator. Charge does not move easily through the air, except lightning is charge moving through the air. Lightning is a wonderful, beautiful thing. Even if something is an insulator, with a lot of effort, let's say, we can get the charge to move through it. So everything is a conductor. It's just, is it a good conductor or a bad conductor? Does it conduct charge? Does it allow charge to move easily or not so easily? So I just want you to know that conductor and insulator are relative words. There is a spectrum rather than it's A or B. It's not an A or B thing. It's a spectrum kind of thing. All right, that is all I have for you today. Thank you so much for listening in. I hope you have a great day, but whatever you do, don't break the laws of physics.